So first, let me say thanks to um, the organization for putting together what's been an interesting week of um, historical talks. And thanks also for putting me last so that I can rely on um, the previous talks to fill in some of the details that I won't have time for. Um, but not to worry if you haven't been following along with the talks all week, because what I will say will be largely self-contained. So uh, the the talk is going to proceed in roughly three equal parts. The first, in the first, I'll review the structure of theoretical physics as it's de developed over um, the centuries, um, and then I'll introduce string theory and why it represents a departure from that standard paradigm, and then talk about one particular aspect that I was involved with, which is the heterotic string. So, um, so So what is it that theoretical physics is supposed to do? What we hope for is some sort of conceptual framework that allows us to um, explain the world we see around us, as well as to develop some quantitative language, mathematical framework for describing those concepts, in which we can do quantitative calculations. And so what I'm going to talk about is a history of those ideas and how they led to the development of string theory as a quantum theory of all the fundamental forces, including gravity. And we'll see that while string theory grew, in some sense, organically out of that framework, it represents something of a radical departure. And as we'll see, there are several there was what's sometimes called the first superstring revolution that happened in the span of less than a year in the academic year 1984-85, which our goal is to get to. So what's the paradigm of theoretical physics? Well, since basically Newton, we specify a set of dynamical variables that characterize the state of some dynamical system, and those variables that parameterize the state of the system have some domain in which they live, and that domain is the configuration space. A point in the configuration space is a state of the system. And so the goal is to, given some initial state, to determine the evolution of the state thereafter. And that takes place via the principle of least action, which determines the evolution via the variational equations, the Euler-Lagrange equations, which is just a repackaging of Newton's laws of motion. And this way of thinking about things extends to the quantum theory via Feynman's path integral. That is, that the action determines a complex phase, and by summing over all possible trajectories, we fill out the quantum wave function and its evolution. Now, while this formalism was initially developed for describing ordinary objects like masses and springs, trajectories of projectiles, and motion of the planets, it far exceeds that limited framework for which, or limited set of circumstances for which it is developed. In particular, Maxwell's theory of electrodynamics and Einstein's general relativity fit within this standard paradigm. So let's go through how that works for electromagnetism and for gravity in brief. So in Maxwell's theory, the dynamical variables are the gauge potentials from which you can derive the electric and magnetic fields. And in the quantum theory, this vector potential provides a basis for comparing the phase of the wave function of a charged particle as we transport it around in space and time through the Bohm-Majorana phase, which says that the physical change of phase as you move a particle around from point to point in space-time picks up a phase that's determined by the vector potential. And similarly, in Einstein's theory of gravity, the underlying dynamical variable is a so-called metric tensor, which just specifies the physical distance between points in space-time by taking a coordinate displacement and contracting it with the energy with the metric tensor, and then integrating up the result to determine the physical distance. And so if you know the physical distance between points, you know the geometry of space-time, which is what Einstein's theory is all about. Now, coming together with these two physical specifications of phases of wave functions and distances between points is a notion of local symmetry. And that local symmetry ensures the conservation of properties of matter, such as charge and energy and momentum. So for instance, Einstein's equivalence principle says that an astronaut orbiting the Earth in some spaceship feels weightless. Well, they're in a gravitational field, the gravitational field of the Earth. On the other hand, they don't feel locally any net force due to a cancellation between the centrifugal force of their orbital motion and the gravitational field. So he reasoned that those two effects must somehow be equivalent, hence the name of the equivalence principle. But the frame of reference is just a choice of coordinates for parametrizing events in spacetime. And so indeed, if you look at the physical distance between points that I wrote on the previous slide, it is invariant under changes of coordinates. So if you replace the coordinates parametrizing points in spacetime by some other coordinates, then the physical distance is invariant under that change of coordinates. And in Einstein's theory, this metric tensor that specifies the geometry of spacetime is the gravitational field. Similarly, if we look at Maxwell's theory, the phase difference between 2 points in space-time is given by the path phase that I wrote down earlier. And if I want to, think about interference effects between different trajectories, as for instance you would see in, say, some sort of Stern-Gerlach experiment, or interference effects in quantum propagation, that difference in the phase between different trajectories is just the difference of these two path phases, and that's quantity is invariant under a local shift of the vector potential by the gradient of a scalar. And so it's a short path, it's a short sequence of manipulations to go from these local symmetries under shifts of the vector potential and the metric tensor to the conservation laws, and that sequence of steps was worked out by Emil Martinec around the time of the development of general relativity. And so in particular, this local gauge symmetry is deeply related to conservation of electric charge, and the local coordinate invariance of Einstein's description of gravity is deeply related to energy momentum conservation. So how does that work in a little bit more detail? Well, Noether's theorem relates the local symmetry principle to a locally conserved current that carries the conserved quantity. So for instance, in electromagnetism, that's the electric current 4 vector. And in the case of Einstein's theory of general relativity, it's the energy momentum current, or if you like, the energy momentum tensor that you build out of matter. So for instance, if you look at charge conservation in some region of space-time, then the time rate of change of the charge that's enclosed in that region, charge can't be destroyed, it's conserved. And so whatever charge you have, the amount of charge you have in the region, the only way it can change in time is if it flows in or out of the region. And so its time rate of change of the charge is related to the flux of charge through the boundary of the region. And so if you shrink the region down to a tiny point, that conservation law becomes an equation of conservation of the related current. It says the time rate of change of the charge density at a point is related to the divergence of the electromagnetic current. So when fields like electromagnetism or gravity are quantized, they manifest the wave-particle duality of quantum mechanics. That is, in quantum mechanics, the wave function describes propagation of matter from point to point, and then if you evaluate the wave function at some point, it gives you the probability amplitude for finding the particle at that point. And so in quantum field theory, the field, the vector potential in electromagnetism or the gravitational field in Einstein's theory, is the quantum mechanical amplitude to find a particle associated to that particular force. So for the electromagnetic field, the amplitude, the vector size of the vector potential, the magnitude of the vector potential at a point is the amplitude to find a photon at that point. And similarly, the metric tensor describes the quantum mechanical amplitude to find a graviton at some particular point. And the symmetry currents, the electromagnetic current and the energy momentum tensor, are built out of the matter fields. For instance, in the standard model, the matter particles are electrons, quarks, neutrinos, and so on. And so you build these electromagnetic and gravitational currents out of the fields that are associated to those particles by wave-particle duality. And we know that matter particles have additional conserved quantities that they can carry in addition to charge and energy and momentum. In particular for quarks, they carry the three-component color charge of the strong interactions, so-called quantum chromodynamics. And similarly, the particles of the standard model transform under weak interactions by a so-called weak isospin symmetry. And those local symmetries then are associated to new kinds of vector potentials associated to those forces. And the resulting theory is what's known as Yang-Mills gauge theory. So the standard model of particle physics then is characterized by its local gauge symmetries, phase rotations for electromagnetism, two-component complex rotations for the weak interactions, and three-component color rotations for quantum chromodynamics, together with the matter fields that carry those charges. And so once you've written down the theory, like any quantum mechanical theory, one thing to try is to do perturbation theory in some interaction strength. In the case of electrodynamics, that works very well, where the dimensionless coupling strength is the fine structure constant, which is approximately 1/137. And so you can go calculate, scattering processes using that perturbation theory, as you would in any quantum mechanical theory. But one thing that one needs to worry about is that there are more degrees of freedom in the field theory, if you just quantize it straightforwardly, than there are physical states of the electromagnetic field. So, physical wave solutions of the quantum electromagnetic field are photons, and they only have two physical polarizations. On the other hand, the vector potential has four polarizations, four choices of the index of the vector potential, and so that's too many. And so the question is, how do you so there are sort of two physical polarizations, two unphysical polarizations. How do you keep the unphysical polarizations from contaminating these scattering processes and leading to unphysical results? And so in electromagnetism, that's pretty straightforward. It was done in the 1950s. But doing the same thing in the weak interactions, QCD and gravity, is more complicated. Basically, the point is that the photon is not charged. So it itself doesn't carry electromagnetic charge. And so it's fairly straightforward to quantize the photon field um, and separate out um, um, these physical and unphysical polarizations. But for QCD and weak interactions in gravity, the gauge fields, the gauge particles, the gluons, say, of QCD, are themselves charged under the strong force. And so you can have processes where a gluon propagating along splits into another pair of gluons. And so you have to, and because this is a quantum mechanical process, you have to sum over all the possible intermediate states that can occur. And so in particular, if you have four components of the gluon field and two of them are unphysical, then what's to prevent the unphysical polarizations from contaminating this intermediate state? And so you have to deal with that in some way. And that wasn't understood for more than a decade until Fadeev and Popov introduced the notion of auxiliary ghost fields, whose role is basically to cancel out the unphysical components of the gauge fields in intermediate states. So if you have a physical polarization of gluon coming in, you can allow all the polarizations, including the unphysical ones, to flow through the intermediate channel. And then if you sum the amplitude for that process with the amplitude for the same gluon to split into a Fadeev-Popov pair of Fadeev-Popov ghost fields, then the sum of this amplitude and this amplitude cancels the unwanted polarizations here against the ghost contributions from the extra diagram. And so it's basically like an accounting tool to keep track of physical excitations of the gauge fields as they propagate around in space-time and ensure that in a physical process, only the physical polarizations net contribute to the quantum mechanical amplitudes. And so this seemingly technical accounting tool was very convenient mathematical trick for ensuring that scattering processes obey all the requirements of Lorentz covariance, charge conservation, energy momentum conservation, unitarity, et cetera, that you would want in a consistent quantum theory. Okay, so that's the sort of the framework of theoretical physics, in particular the particle physics of the Standard Model and Einstein's theory of general relativity, as it existed in the early 1970s, as you've heard in talks that were given earlier in the week. Now, string theory grew in essentially a rather different way. It came from trying to understand what was going on in the strong interactions. You know, the thing I've just presented to you, that the strong interactions are governed by quantum chromodynamics, which is a gauge theory very similar to Maxwell's electrodynamics. That was a kind of that was arrived at after a lot of sort of false starts. Because the strong interactions are strong, you turn on an accelerator, you get copious production of strongly interacting particles. And it seemed like every time a new accelerator was turned on in the late 50s, early 60s, with a little bit higher energy, center of mass energy than the previous one, you got new sets of strongly interacting resonances. And it seemed pretty hopeless to describe all those resonances by giving them, each matter particle in an intermediate state would then have to have its own quantum field. And the number of quantum fields were then just proliferating like crazy. And it seemed like there wasn't any kind of endpoint to this process of finding new resonances, introducing new fields, new interactions. The whole endeavor seemed like it wasn't, kind of reaching a finite conclusion. And so along came string theory as a way, as a kind of an organizational framework for understanding why there were all of these resonances. If you plot the various intermediate state resonances in the appropriate variables, you find that they lie on some kind of nice linear trajectories. And it was understood after Veneziano developed his ansatz for what the scattering of those strongly interacting resonances should look like. It was then, not too long, a year or so, before people realized that the underlying principle from which you could derive that Veneziana amplitude was the dynamics of a relativistic string. And so roughly how it works is that the string worldsheet is some generalization of the diagrammatic formalism that describes particle scattering. So if you had, say, electromagnetism and you had some charged particle running along in space-time, the way that charged particles scatter off of one another is by exchanging photons. And so you quantum mechanically sum over all of the matrix elements and the amplitudes for propagation of intermediate states, and you develop a perturbation series for the scattering amplitude. And in string theory, the idea was to replace the particles with a relativistic string, because a relativistic string had the right features to describe the various resonant intermediate states. And so the idea was that if you replace the particle scattering process by a string scattering process, that the possible intermediate states that could appear at some intermediate time would be various excitation levels of the string, which are the various resonant particles. Okay. Now, this then is not quite the same framework that I was presenting to you in the first part of this talk, which was a formalism where you say, let's first write down some sort of symmetry principle. Symmetry principles lead to conservation laws. We look around in nature and see what quantities are conserved. And then we write down a field theory, okay, for which the field is like the wave function of the particle, and the particle is some sort of secondary thing, namely the quanta of excitation of the field. The photon is the quantum of excitation of the electromagnetic field. Graviton is the quantum of excitation of the gravitational field. The electron is quantum of excitation of the Dirac electric field, electron field, etc. Instead, string theory grew out of some attempt to organize directly the results of scattering processes, because it looked like a field theoretic version of the strong interactions wasn't going to be in any way successful, and there sort of wasn't enough structure, it seemed, to go via the field theory route. And so instead, what you ended up with was this description of individual scattering processes as being described by the trajectories and interactions of strings in space-time. And so in particular, there wasn't any action principle, any kind of field theory, any kind of action principle. All there was a prescription for deriving the amplitudes that result when strings scatter. And that prescription was really a description of the dynamics of the individual strings, rather than some kind of dynamics of a field from which the strings were excitations. So what is what version of an action principle is there then that governs the dynamics of the individual strings, as opposed to some kind of field theory action principle as there is in Maxwell or GR? The action principle is quite geometrical. It was written down by Nambu and Goto in the early 1970s. And it's basically the generalization of um, the length of a trajectory of a path. So you recall that in Einstein's theory, the length of a path in space-time is obtained by integrating the gravitational field along the trajectory. You integrate this quantity across the trajectory, and you get the length of the path in space-time. So in string theory, the notion of the length of a path is replaced by the notion of the area of the world sheet that's swept out by the string as it moves in space-time. Okay, so the principle of least action is to extremize the area of that path. And then that extremized surface, two-dimensional surface, would be the trajectory of the string in space-time. And just like Einstein's description of the length of a one-dimensional path in space-time is not dependent on the way you parameterize that path, similarly, this description of the area of the world sheet is invariant under the parameterization of the world sheet. So if you change the if you change the coordinates that you use to label the various points on this 1+1 dimensional trajectory, change that labeling to another labeling, you get the same area, right? Because you haven't changed where the surface is in space-time. You've just changed your description of the points, how you label them. And so just like in Einstein's general relativity, that kind of reparameterization symmetry is associated to a conservation law. In this case, it's the conservation of the energy momentum tensor on the two-dimensional world sheet. Not the energy momentum of the strings in space-time. We don't have a field. We don't have Einstein's gravity yet. We just have this two-dimensional world sheet, and there's a two-dimensional energy momentum tensor that describes energy and momentum on the string. So if I have some wiggle on the string, it propagates along, if I have some normal mode excitation of the string, it propagates along the string world sheet. And as it propagates along, the energy and momentum of that wave along the string is conserved. And that's represented by this conservation law along the trajectory. So that local reparameterization symmetry then eliminates unphysical oscillations of the string. So if we look at the string trajectory and we change the labeling, so the grid of the coordinate grid on the string world sheet is replaced by a reparameterized coordinate grid, that doesn't change the area of the world sheet. It's the same physical surface in space-time. So it has the same area. And so these sorts of changes of the description of the string are unphysical. And so it's that gauge symmetry together with a choice of what's called a gauge constraint, if you like, fixing a particular parameterization, eliminates the longitudinal oscillations, right? Because if I make a wiggle of the trajectory of this sort, it's completely unphysical. It doesn't change anything in space-time. It's the symmetry of the action. Okay, and so only the oscillations of the string that change the trajectory of the string in space-time are physical oscillations. And so if the string is to describe some particular particles, is describing some kind of effective particle states as resonances of the string, only the only the components of oscillation of the string that are transverse to the string's trajectory are physical. Okay. And so so that sounds nice. It would be a way of restricting the physical states of the string to those that are um, uh, uh, are are transverse to the direction of motion, in the same way that the polarization of the electric field of the photon, of the physical state of the photon, is transverse to the direction of motion of the photon. And so, however, it was something of a surprise as people started to look at this more closely, that the proof of the reparameterization and that it eliminates the longitudinal oscillation modes required a certain particular dimension of space-time to work out correctly. And I think this was described in detail in Peter Goddard's talk at the beginning of the week. That is only, there were two types of string theory known at the time, the so-called Niveux-Schwarz-Ramond or fermionic string and the so-called bosonic string. And the bosonic string seemed to only have the required reparameterization invariance if the string was propagating in 26 dimensions of space-time. And the fermionic string seemed to only work in 10 dimensions of space-time. And outside of those particular dimensions, the reparameterization symmetry had what's called an anomaly. That is, what is an anomaly? An anomaly is a situation where if you look at the classical action, say the Nabu-Goto action for that is invariant under reparameterizations of the worldsheet of the string. That's a manifest symmetry of this classical action. However, it turns out that that reparameterization symmetry has problems once you quantize the oscillations of the string. And how can that happen? Well, it can happen because quantum field theories have an infinity of degrees of freedom. If I look at a string, it has an infinity of normal modes. Every wave, if I look at a closed loop of string, right? It has well, if I plot it, it can have one oscillation, two oscillations, three oscillations, and so on. There are an infinite need of oscillation modes of that relativistic string. And since in quantum mechanics I have to sum over all possible intermediate states, when one string splits into two strings, then I have to sum over all of the intermediate states of string. And if those can have an infinite number of possible states of vibration, I have various infinite sums that I have to understand. And so sometimes when, so if you can find a regulator that's compatible with the symmetries of the classical action, you're good, right? Because if you want to regulate those infinite sums in some way, if the regulator preserves the symmetry, then once you appropriately sum things up and take the regulator away, you're guaranteed that the result still respects the symmetries that you thought were there to begin with. If, on the other hand, the regulator doesn't preserve the symmetry, then you have to go check that at the end of the day, the calculation you did has the symmetries that you thought were there to begin with. And you just have to check that by hand. And so this result from the early 70s that the string only seemed to make sense in particular dimensions, and that outside of those dimensions, you had problems with unitarity and positivity of the Hilbert space norm, et cetera, of physical states. That seemed to indicate that there was some sort of anomaly in this reparameterization symmetry. And so so that was understood to be the case. And a byproduct of that proof was a realization that the quantized string spectrum includes massless. So not only did you get that the result that the quantization only made sense in these particular dimensions, but you also got a particular offset in the energy of the ground state of the string, which meant that various excited states of the string, in particular, the first excited state uh, that the string could occupy, that those excited states were massless. So in particular, the massless particles that one found in the string spectrum in these very special dimensions included massless vector particles and massless spin-2 particles. Now, that's not any good for the strong interactions. In the strong interactions, all of the intermediate resonances are massive, right? They're various hadrons, like the pions and rho mesons and so on. And so this result that it only made sense in a weird dimension, and furthermore, there were massless higher spin particles, completely didn't fit with quantum chromodynamics. It does, however, make sense if your theory is not a theory of the strong interactions, but a theory of electromagnetism and gravity, because the quantum of excitation of electromagnetism is a spin-1 particle, the photon, and the quantum of excitation of the gravitational field is a spin-2 particle, the graviton. And so there was a complete sort of rethinking then that took place in the early 70s, culminating in the suggestion by Shirk and Schwartz that string theory, rather than being some kind of effective theory of the strong interactions, was actually something more akin to a unified theory of all the fundamental forces. So while the scattering amplitudes and the gauge symmetry were only seen, so what is string theory? String theory is a prescription for calculating perturbative scattering processes. And so, if you do scattering processes in a fixed frame of reference, in fixed coordinates, the symmetries are not very manifest. And so you have to go check various properties of the S matrix to see that the consequences of the underlying symmetry for the scattering matrix elements are being respected. And so, of course, string perturbation theory is done, with a fixed number of incoming and a fixed number of outgoing particles. So one could check for those particular processes whether the consequences of symmetry were being obeyed, and the answer was yes. Okay, and so the question, though, is, well, how do I know when I look at the next, higher order in scattering amplitudes or scattering amplitudes with more particles? How do I know that those consequences of symmetry are being respected? And part of the answer came from an analysis of Buller and Deser in the mid 70s that if you had a massless spin-2 particle, and at the linearized level, it had the symmetries of linearized Einstein's gravity, that the nonlinear completion had to be general relativity. And so this is the sort of reasoning that fed into this realization that string theory was a theory of gravity rather than a theory of the strong interactions, that this massless spin-2 particle, which at low orders in perturbation theory had the properties of a graviton and its linearized symmetries and correct cubic interactions, that if you worked everything out to all orders in the expansion in fluctuations, that what you would end up with was inescapably Einstein's gravity at least as a low energy approximation. And there's kind of an intriguing connection in the process between the worldsheet reparameterization invariance, which guarantees the absence of unphysical polarizations of string oscillation, and the symmetries that get rid of unphysical polarizations of photons and gravitons. That at least at the linearized level, there seemed to be some correspondence between this reparameterization invariance of the string and the linearized gauge symmetries of electromagnetism and gravity. Um, but as I said, none of this was particularly apparent or manifest in the way string theory was being formulated. It was something that you checked, at certain, to a certain level of approximation. But then, what's the big picture, if you like? What's the underlying principle from which all of these features follow? Okay, so as I said, the first excited level of the string seemed to be these photons and gravitons. Well, okay, if that and those were massless, then well, what about the ground state of the string? If that has to have lower mass than the first excited level, and so it was seen that that ground state, that negative mass squared ground state, was hard to avoid. In particular, for the bosonic string, it's pretty much unavoidable that there is such an unstable ground state. Okay. So in physicist jargon, they call this a tachyon. Physicists use all kinds of bad terminology for describing physics. This is an example because tachyons originally came up as particles traveling faster than the speed of light. No. In this context, tachyon means instability, that the vacuum of the theory is unstable, and if you give it a little kick, the theory runs away, and all of these instabilities proliferate in spacetime, and what you thought was Minkowski spacetime gets filled with all kinds of unstable fluctuations of strings. And so the 26-dimensional bosonic string is not a viable theory of anything because it doesn't have a ground state, or at least it doesn't have a weakly coupled Minkowski spacetime vacuum ground state, which is a good approximation to the world we see around us. Things were a little bit better for the fermionic string. There is such an instability. There is a massless spin 2 particle at the first excited level, and the ground state looks like it has a tachyon. But you can find a way of removing that instability, that unstable string mode, by imposing a symmetry. So there's a discrete global symmetry known as the GSO projection. And if you select the set of states that are invariant under this symmetry, well, the tachyon mode, the unstable mode, is not invariant under the symmetry. And so if you say, I want to impose this one additional symmetry, this GSO symmetry, then the tachyon is not invariant under that symmetry, so it's removed from the spectrum. And if you keep only the states that are invariant under the GSO symmetry, and add a complementary set of excitations, which also respect the symmetry, then the theory turns out to be stable. In fact, it has a new symmetry that wasn't there before you implemented the GSO projection, which is the so-called supersymmetry. The states you have to add are the fermions in spacetime, and it's a good thing that you then have to impose this symmetry because you want there to be fermions in spacetime, like electrons and quarks and neutrinos. And so it's a good idea to impose this symmetry because it introduces the fermions into the string excitation spectrum. And furthermore, it introduces a symmetry between the bosonic and fermionic states of the string, which is supersymmetry that was also being developed in the 1970s. Now, so I've been portraying this idea of string theory as fitting into some kind of standard story of anomalies as it was developed in quantum field theory in the late 60s and early 70s. But that really wasn't the way that people at the time thought about what they were doing. Instead, they were focused on these sums over intermediate states and the infinite sums that were arising, delicate procedures of regulating those infinities and then subtracting out and renormalizing processes, and looking at what you got left over and asking if it satisfied various um, properties that one would need to have. And that way of proceeding made it look like what was going on was some very delicate dance of looking at infinite sums that were coming up in the sum over intermediate states and trying to make sense of them, and so on and so forth. And so it seemed, very kind of black magic. Where did this 26 come from? Where did 10 come from? And it just came as as the output of some very, convoluted, calculation. An example of which I've given here, that, one of the divergent sums that one needed to make sense of was the sum over the ground state energies of all these harmonic oscillation modes of string vibration. And so you get a half h bar omega for each vibration mode. But if you have, the lowest harmonic, the next harmonic, etc., the half h bar omega of all of those things is basically a sum over all the positive integers. And that's divergent. And so one way you can make sense of that divergent sum is to regulate it by treating it as some kind of analytic continuation of the Riemann zeta function, which converges for s bigger than 1. And so if you say, okay, let me define it as a function of s for the values for which it makes sense, and declare that the regularized and subtracted version of what I'm getting out of the string calculation is just the analytic continuation of that to other regimes of the parameter s, which I need for the calculation. And so, okay, so the Riemann zeta function is some nice, perfectly analytic special function of mathematical physics. And so zeta minus 1 is minus a 12th. This is the origin of the ground state energy of the string being, mass squared being negative, is this particular calculation. And so, as I was saying, that it looked kind of magical, okay? That you regulate the sum over the 0-point oscillation energies of all of the string vibration modes. That's some infinity. Once you get rid of that infinity in some standard way, what's left over is a residual energy for the ground state mass squared, and that turns out to be negative, and that's why the ground state of the bosonic string and the fermionic string appears to be a tachyon. Okay, but I as I say, the modern perspective is that all of this is a consequence of reparameterization symmetry. So how does that work? And basically now I'm getting towards the modern viewpoint. So in the mid 70s, Brink-Devecki and Howe and Dazer and Zumino ask themselves the question: if the action for a string is, if the fundamental symmetry principle of the worldsheet is reparameterization invariance of the parameterization, reparameterization invariance of the worldsheet action under worldsheet reparameterizations, the way I coordinatize the trajectory. Well, we have a standard language for describing reparameterization invariant things. That's Einstein's GR. And so let's use the language of Einstein's GR, not applied to space-time, but applied to the worldsheet. And so they said, okay, let's write down a standard generally covariant action for the dynamics of the string, where we introduce a metric in the same way that Einstein introduced the metric tensor to describe space-time gravity. You could describe worldsheet physical distances along the worldsheet by introducing a metric tensor on the worldsheet. It's not a metric tensor in space-time. I'm using different labels A and B instead of mu and nu to distinguish when I'm talking about A and parameterizations on the worldsheet. I'm using Latin indices. space-time, I've been using Greek indices. So this is just something that tells you on the world sheet of the string, what's the distance between 2 points on the world sheet. Okay. Same sort of way I was describing things for space-time and trajectories in space-time. And so then they wrote down the natural action principle for string coordinates that had a reparameterization invariance. And then you will notice that this reformulation of the theory had the same classical solutions as the Nambu-Goto action that I wrote somewhat earlier. And so it's a classically equivalent description of a relativistic string. But its nice feature is it has one additional symmetry which wasn't manifest in the Nambu-Goto formulation, which is a local scale invariance. That is, if I rescale the metric, I rescale the distance between points by an overall scale transformation. And that turns out to be a symmetry. The determinant of the two-dimensional metric is the determinant of a 2x2 matrix. And this is the inverse of that 2x2 matrix. And if I perform this rescaling, the scale factor just drops out. It cancels between this factor and this factor. And so this way of reformulating the dynamics of a relativistic string has the advantage that it has somewhat more symmetry than the Nambu-Goto formulation. And conservation of the local scale current is equivalent to the tracelessness of the energy momentum tensor associated to this local reparameterization invariance of the string world sheet. So a little bit later, Polyakov married this GR-style description of the relativistic string with the Faddeev-Popov formalism that I mentioned earlier as a way of describing the measure for integrating over the symmetries. And so Polyakov wrote down the Brink-de-Vecchia-Hau-Deser-Zumino action, quantized it, and in the process of quantizing it, introduced as well the Faddeev-Popov ghosts associated to the local reparameterization symmetry. And what he saw was that there was an anomaly in the conservation of local scale invariance. What you thought was the expression, so local scale invariance, again, is the tracelessness of the energy momentum tensor. And what Polyakov did was he calculated the leading quantum fluctuations of the string coordinates and found that there was a non-zero right-hand side to the trace of the energy momentum tensor. So for every coordinate of space-time, there was an amount of 1/12 of violation of scale invariance symmetry. And so this is an example of an anomaly. What you thought was a classical symmetry, this local scale invariance, is now not a symmetry in the quantum theory. And he also showed that quantizing the fluctuations of these Faddeev-Popov ghosts led to an additional contribution to the trace of the energy momentum tensor of -26. And so this, starting with Polyakov, the way we understood this specific dimension for the bosonic string is that it's the dimension of space-time in which all the anomalies cancel between the Faddeev-Popov ghost fields and the string coordinates, leading to the classical symmetry of scale invariance being also a symmetry of the quantum theory. And then if you do the analogous calculation in the fermionic string, that has a slightly different symmetry, local supersymmetry along the world sheet, and quantizing the string coordinates together with their Faddeev-Popov ghosts leads to the result d equals 10. And just as a little side note, my first research project as a graduate student was a technical exercise in the application of Polyakhov's formalism to the fermionic string. Okay. So the restriction of space-time dimension comes from the cancellation of the anomaly in local scale invariance. And in fact, Polyakhov's motivation was that he wanted to evade this conclusion that strings were only consistent in 26 dimensions for bosonic strings and 10 for fermionic strings. And so I think the more precise statement of his result is that if you want the space-time to be empty, the background in which strings are propagating to be empty Minkowski space-time, then that's only a solution of this scale invariance condition for d equals 10 or 26. We'll return to that point a little bit later. So next step in the development, at least for me, was a set of summer school lectures given by Dan Friedan in 1982 in Les Houches, where I was fortunate enough to be a student. And he reformulated Polyakhov's calculation using the tools of complex analysis, which are available to you in 2 dimensions, using specific coordinates that are adapted to the fact that the complex plane is a 2-dimensional manifold. And related the local scaling anomaly to the anomaly of conformal symmetry. So what are conformal transformations? They're reparameterizations that are also local scale transformations. So there's not a clean separation of this local scale symmetry from the reparameterization symmetry. So if you have an anomaly in one, you have an anomaly in the other. And so it was through this chain of logic that one realized that the lack of local scale invariance led to the lack of reparameterization invariance, led to the lack of decoupling of unphysical polarizations of strings. And the nice feature of Friedan's calculation was that it emphasized how the anomaly, it wasn't phrased in terms of delicate calculations of divergent sums, or in Polyakhov's calculation, it was delicate regulation of some functional determinants in the path integral measure. It was just looking at the ward identities, the consequences of symmetry in the operator algebra, and a little bit of use of conformal symmetry to realize that things wouldn't work out unless you were in this very specific dimension. And around this time, Polyakov, following up his work on reformulating the string, was interested in developing then these ideas of conformal symmetry in 2-dimensional field theory. And that led to this landmark paper of Belavin, Polyakov, and Samologikov. It was discussed both by John Carty and Greg Moore in their talks earlier this week. And so I have to, at this point, unfortunately, I couldn't find any way of presenting all these developments in some kind of sequential, chronological order. And so at this point, I need to back up a little bit to talk about Daniel Friedan's thesis, his graduate thesis, which he produced in 1979. And he was interested not in so much in string theory, at least it's not apparent in his published the published version of his thesis, so much as just some kind of abstract question of 2-dimensional field theory. That is, if I look at some general 2-dimensional field theory describing scalar field theories parametrizing some curved geometry, then what's the behavior of what are the properties of that quantum field theory under Wilsonian renormalization group transformations? What do scale transformations do to the generic 2-dimensional field theory? And so what he showed was that there is a separate violation of scale invariance apart from the conformal anomaly, that if we have scalar fields, two-dimensional scalar fields parameterizing some curved embedding space, that two-dimensional field theory has a separate violation of scale invariance, which is related to the curvature of the manifold on which the scalar fields that the scalar fields are parameterizing. And so this was just a pure two-dimensional field theory statement. But when you apply it to string theory and demand that this local scale invariance be preserved, it leads to the vanishing of the Ricci curvature of the ambient geometry. And so of course that's equivalent to the vacuum Einstein equations. And so there seemed to be some connection to Einstein's general relativity and this condition of local scale invariance. So it's really worth pausing to just think for a moment how remarkable that is. If we take Friedan's result, which is just a pure two-dimensional field theory renormalization group calculation, and you apply it to string theory, that is, you say, I want strings propagating in some curved manifold, and I ask that the string propagation be self-consistent, that the unphysical polarizations of string drop out, then that only works seemingly if all you have turned on is curved geometry. It seems to only work if the spacetime in which the string is propagating satisfies Einstein's field equations. And this wasn't put in from the beginning. It just simply emerged from demanding consistent propagation of the string, that there are no unphysical effects in string propagation in this ambient spacetime. Of course, string theory, as it was realized by Shark and Schwartz, has additional gauge fields besides the metric of general relativity. And so one could ask, what happens, how do I understand those other fields? Those other fields have field equations, where did they come from? And so several groups in this remarkable period of the academic year, 84, 85, started looking at that question. And so, among the massless fields in string theory are the metric of general relativity, an antisymmetric tensor gauge field, which is the gauge field under which the string is charged. So the string carries, in some sense, electric charge under this higher rank tensor field. And then there's a scalar which specifies the strength of string interactions. And so, you could say, okay, if I write down the action principle, the worldsheet action principle, whose variational equations are the classical trajectory of a string in the spacetime specified by these fields, what's the condition for scale invariance of that quantum field theory? And so there was some lead-up work by Fredkin and Seitlin, and then contemporary work with Ashok Sen to work that I did with Callan and Dan Friedan and Malcolm Perry, for which the output was a set of what are called beta function equations for the conditions for tracelessness of the worldsheet energy momentum tensor on the string worldsheet. And so we can expand out the trace of the energy momentum tensor in a basis of local operators, say the gradient squared of the field, the symmetric part of the gradient squared, the antisymmetric part of the gradient squared of the string embedding. And then this term that has to do with the Polyakhov's anomaly. And each of those has a coefficient function, which is some function of the data specifying the background, the spacetime fields G, B, and phi that are part of the string spectrum. And so the condition for local scale invariance are the separate, since each of these operators is an independent operator in the spectrum of operators, in order to have a scale invariant field theory, each of the coefficient functions of each independent operator must vanish. And so you look at the equations that you get by analyzing the renormalization group of this general two-dimensional field theory. And what you find is, indeed, the Einstein equations, together with the correct stress energy tensor in Einstein's field equations that come from the fields B and phi, the dilaton equation that results from the vanishing of the coefficient of the intrinsic curvature of the worldsheet imposes the space-time dimension conditions. This equation, the vanishing of this quantity, is the equation of motion for this antisymmetric tensor field. In other words, all of the dynamical equations that you would expect the space-time theory to have are consequences of this one overarching condition of local scale invariance of the string dynamics. So, so what about an action principle in space-time? That's been completely absent from what I've described to you so far. It's kind of a byproduct. It's the statement that Einstein's equation and the antisymmetric tensor field equation and the dilaton field equation, the equation for motion for this scalar field phi, which is called the dilaton, those all follow from an action principle, right? The Einstein-Hilbert action, generalization of Maxwell for the B mu nu field, separately a scalar field action for the dilaton phi. Those all come, those are, those equations of motion that are the beta function equations, those come from an action principle in space-time. And so it's sort of a byproduct that the renormalization group flow, the thing that the beta functions tell you are the local violations of scale invariance, those equations, the vanishing of beta G, beta B, and beta phi, those come from the variation of a space-time action principle. And so the renormalization group flow that's specified by the beta functions is what you might think of as a gradient flow. That is, the gradient of the space-time action, the Einstein-Hilbert action, et cetera, with respect to the space-time fields G, B, phi, specify a motion in the space of quantum field theories, for which the fixed points of those flows are the scale invariant theories, and the scale invariant theories are the solutions of the Einstein and matter field equations. Okay. So that about wraps up what I wanted to say about sort of the underlying symmetry principles of string theory, and how to think of string theory as kind of a different approach to describing the fundamental theories of physics. Except for one point I'd like to tie up, and it relates to other work that I did with Friedan and Schenker, which is, and this is something that was described a bit by John Carty, that it was understood from the early days that conformal invariance, the so-called Virasoro algebra, which is the algebraic realization of conformal symmetry, is associated to a whole structure of the operator algebra, that the operators and the states of the theory lie in representations of the conformal symmetry algebra. And in particular, that there's a state operator correspondence. That is, that the two-dimensional field theory that describes the string worldsheet has some vacuum. And if I'm interested in any other physical state of the string, it's related to the vacuum state by applying some physical operator. That is, the physical operator serves as some kind of physical operators, states that can conformally invariant operators create physical states by acting on the vacuum. And furthermore, that the scattering amplitudes are given by correlation functions of these physical state operators. So in particular, the various S-matrix amplitudes as described by Veneziano and by Virasoro-Shapiro and Koba-Nielsen in the early days of string theory, as described, for instance, by Peter Goddard. Those amplitudes are are simply the conformally invariant observables in this scale invariant field theory. Now, space-time supersymmetry requires that half of the physical states are fermions. And what wasn't understood in the early days, I think Peter Goddard touched on this briefly, was how to construct the scattering amplitudes of space-time fermions. The technology that was available in the early 70s was extremely cumbersome, all these infinite sums and so on. And it seemed like you had to introduce various factors by hand in order to have a sensible fermion scattering amplitude. And so in work that I did with Friedan and Schenker in the spring of, that led to a publication in the spring of '85, we worked out those finishing details. And what we saw was that, ordinarily, the reason one was able to get by for 10 or more years describing string theory without thinking about the Fadeev-Popov ghosts for reparameterizations was that they largely decoupled from any physical process. But what was seen with the fermions was that the conformally invariant operators that create physical fermions from the two-dimensional field theory vacuum, those operators intrinsically involved a contribution from the Fadeev-Popov ghosts, that if you ignored that contribution, you got nonsensical results. And so what we produced was a recipe for constructing the full spectrum of physical state operators in Minkowski spacetime, including the fermionic states and operators, a prescription for how you would extend that spectrum of operators and states to general spacetime backgrounds, solving the beta function equations, using the conformal field theory methods that were developed by Belavin, Polyakov, and Samologikov, and proving that the ghost formalism, the so-called BRST formalism for calculating in theories with Fadeev-Popov ghosts, led to a proof of the gauge invariance of the perturbative string S matrix, as well as mechanisms for seeing how linearized gauge symmetries propagated to the full string S matrix. The space-time linearized symmetries led to, at the level of arbitrary scattering amplitudes, space-time gauge invariance. And so, and the nice feature of this synthesis was that the rules are surprisingly general. That in some sense, a solution to string theory is any collection of two-dimensional conformal field theories that have the right properties, the right vanishing of the conformal anomalies, and the existence of this GSO projection that allows you to get rid of the instability of the space-time vacuum. And so a lot of these theories, so you could, for instance, take the minimal models that John Carty was talking and Greg Moore were talking about in their lectures. And you could just tensor together a bunch of those. That would make a conformal field theory of the right, that satisfies all the anomaly cancellation conditions. And there's no reason to reject that as opposed to having some nice, smooth, macroscopic space-time manifold. So this sort of Einstein's, theory of, smoothly varying manifolds describing, a background for string propagation is itself part of a much more general story of which these worldsheet symmetry conditions, tell you what the organizing principle is that describes all of them. Okay. So in the time I have available, then I'd like to describe the third project that I was involved in during this time period of academic year 84-85, which is the development of the heterotic string. And so I've described the worldsheet anomalies having to do with local scale invariance. The standard model itself has anomalies. The standard model of particle physics has a chiral spectrum, the left-handed and right-handed polarizations of electrons and quarks um, uh, um, have different gauge charges. And there isn't any regulator that we know of that preserves all of the local symmetries of the standard model. And so once again, one has the potentiality for having some sort of anomaly that prevents what you thought of as being the classical symmetries of the Yang-Mills plus matter Lagrangian from being an actual symmetry of the quantum theory. And um, and so practical consequence for this for the weak interactions is that the non-anomalousness of the standard model is a delicate cancellation between the contributions to the anomaly from different species of matter particle. And this was, for instance, one could say that the existence of the charm quark was predicted from the known spectrum in work of Glashow, Eliopoulos, and Maiani in the early 70s, was predicted on the basis of anomaly cancellation, that if you didn't have an additional quark, you wouldn't have the right spectrum of charges for the weak interactions to be free of anomalies. So in the early 80s, around the time that string theory was getting going as a theory of the fundamental interactions, Alvarez, Gomez, and Witten analyzed the anomalies of 10-dimensional supergravity, of which string theory is some kind of ultraviolet completion. And what they showed was, well, so this is the key statement from the abstract of their paper. They showed that in the 10 dimensions, there is a unique theory with chiral spectrum and anomaly cancellation. And it's the chiral n equals 2 supergravity theory, which is the low energy limit of one of the superstring theories. Beyond 10 dimensions, there's no way to cancel those anomalies. And so it was an interesting result in the sense that something seemed to be picking out string theory as being relatively unique, at least in the dimensions that string theory was thought to be consistent. But unfortunately, that 10-dimensional chiral theory didn't contain the gauge fields that you would need to realize the standard model of electroweak and strong forces. And so enter, about a year later, Green and Schwartz, who found a loophole, if you like. They found a new mechanism for anomaly cancellation and showed that there was an additional string theory having a consistent chiral spectrum. And this was the so-called open string theory, where the gauge forces arise from strings that are not little closed loops, but rather open intervals. And the way that the gauge symmetry was realized was that the endpoints of the open string were charged under the gauge forces. And so the existence of the open strings, in addition to the closed strings that describe gravity, led to a chiral theory that, using this new anomaly cancellation mechanism of Green and Schwartz, was a self-consistent quantum theory. But in the same way that string theory only seemed to make sense in 10 dimensions, the open string theory only made sense, only was free of anomalies for the gauge group SO32. In other words, these charges at the endpoints had only 32 independent values, similar to the 3 colors that you have in QCD. Now, around this time, I arrived in Princeton as a freshly minted PhD, still very much wet behind the ears. And I remember, I arrived at, roughly speaking, 1st of September, 1984. And Green and Schwartz announced their result basically a week or two earlier. And I remember when Witten found out about it, he was extremely excited, that there was this possibility that there was a string theory that could encompass both Einstein's general relativity and the standard model. Now, However, in the course of studying this new anomaly cancellation mechanism of Green and Schwartz, he, together with Jeff Harvey and Jeff's PhD student at the time, Lance Dixon, realized that the anomaly cancellation conditions are something that's polynomial in the various charges of the matter particles and the gauge fields and so on. And in studying those anomaly cancellation polynomials, they saw that there was a second solution to the anomaly cancellation conditions, namely the gauge group E8 cross E8. And so just say that in sort of the classification of continuous symmetries, so-called Lie groups, there are four infinite families, so-called classical groups, such as the unitary groups that are rotations in complex spaces and complex vector spaces, and the rotation groups, the orthogonal groups that are rotations in real vector spaces. And then there are five exceptional continuous groups, of which E8 is the largest and in some sense the most exceptional. But there was a no-go theorem that said that this was not possible in open string models, that if you tried that, there's no charge that you could put on the endpoints of a string that would realize these exceptional symmetries. And so a key question arose is that, well, it seemed like, there was the closed string theory that Alvarez, Gohei, and Witten had investigated. There was this SO32 open string theory that Green and Schwartz came up with. And both of those were associated to consistent string theories. So there's another solution to the anomaly cancellation conditions. Is there an associated string theory? Is the corresponding supergravity theory the low energy limit of some new string theory? And one reason this was potentially of interest is that E8 seemed to be a more promising route for embedding the standard model in some kind of higher symmetry. And so initially, I started working after I read with Jeff Harvey on this question, because Jeff had earlier on had done work in unification using exceptional groups as a grand unification principle of the standard model. And I had some background in string theory from my graduate work on the Polyakov formalism. And David Gross was, one of the senior faculty in Princeton at the time, and he had, expertise in string theory stemming from before he made the transition to QCD and developing asymptotic freedom. He had been, trained in the school of Jeff Chu at Berkeley on, bootstrap and S matrix and string dynamics. And David decided to teach a special topics course on string theory that fall. And ordinarily when you go to a graduate seminar, an advanced graduate seminar, you can fit the people around the conference table. But this course was heavily oversubscribed. Basically, all the graduate students, most of the faculty, and all the postdocs were attending this course, and so it was moved to the large lecture hall, if I remember correctly, in Jadwin Hall. Anyway, although Jeff and I initially started working together, we also then joined up with David, and the three of us started working together to try to find this E8 string. So at some point, a few weeks in, I remembered that as a graduate student, I spent the last part of my graduate career at SLAC in Palo Alto. And while I was there, I attended a 1983 math physics conference in Berkeley on what are called vertex operators, these conformally covariant operators that were discussed by Peter Goddard. And Goddard and Olive presented their work. So Friedan and Schenker were there describing their work on minimal models that you heard about in recent lectures. And Goddard and Olive were there presenting their work on how to realize group symmetry using the same sorts of operator algebra as one uses to construct string scattering amplitudes. And that idea, the core of that idea goes back to the early days of string theory. But they developed it much more systematically. And the basic idea is that any Lie group in Cartan's classification has an associated Cartan torus. And the operator algebra of strings propagating on that torus organizes into representations of the symmetry group. And in particular contains the set of currents associated to charge conservation and gauge symmetry. So I was just some graduate student, not knowing anything, but I went to this conference, and I was intrigued enough about Goddard and Olive's talks that when the preprint came out of writing up their work, came into the Slack library, I brought it with me. Well, I read it. I didn't steal it, as Greg Moore was talking about yesterday. I made a photocopy, and it stuck with me enough, that when I was packing up my belongings and moving to Princeton for my postdoc, I didn't just chuck it in the garbage. I brought it with me, and so I remember this preprint, and and lo and behold, it called out special properties of the groups SO32 and E8 cross E8. And so this had to be on the right track. I mean, we didn't know quite how to fit it into the framework of string theory, but it obviously had to have something to do with the anomaly cancellation that was observed by Green and Schwartz. And so we looked very carefully at their construction and how it worked. And so we tried various ways of fitting the Goddard-Olive construction into a consistent string theory, but it seemed like there was one big obstacle, which is that the E8 cross E8 or SO32 current algebra symmetry that you would need for space-time gauge theory and its anomaly cancellation seemed incompatible with the supersymmetry that you would need to eliminate, and the GSO projection that you would need to eliminate tachyons, the instabilities of the vacuum. And so at some point, I remember talking to Ryan Rome, who was a graduate student of Edward Witten's at the time, and he explained to me some ideas he was exploring using different spectra of left-moving and right-moving excitations on the string. So if you have a closed string and you make some wiggle on it, it either travels with the speed of light to the right or it travels with the speed of light to the left. And those left-moving and right-moving oscillations largely don't talk to each other. They're independent up to some global considerations. And so there it stood. I sort of filed that away. And then a few days later, I was in my apartment in Princeton about to fall asleep and realized that, well, if the left-moving and right-moving degrees of freedom are largely independent of one another, why not take one set of degrees of freedom to be the bosonic string and the other set to be the fermionic string? And so then, this impasse that we were having, that you needed the bosonic string to get the group symmetry, but you needed the fermionic string to get the consistency of supersymmetry and the absence of instabilities, that those two could coexist by having the chirality of, say, right-moving degrees of freedom having supersymmetry. That eliminated the instabilities. Having the left-moving degrees of freedom realizing this Goddard-Olive construction could lead to the gauge symmetry that one needed for anomaly cancellation. And the difference in the dimensions between the bosonic and the fermionic string, namely 16, was the dimension of the Cartan torus of E8 cross E8 or SO32. So the bosonic string propagating in those 16 extra dimensions precisely realized the needed gauge symmetry. Well, needless to say, I didn't sleep any more that night. While at first sight, it seemed like completely loony. I couldn't find any obvious inconsistencies. All the anomalies I could think of seemed to cancel. Right? The Faddeev-Popov ghost determinants for the right-moving degrees of freedom cancel the 10 right-moving coordinates of the fermionic string side. Similarly, for the 26 dimensions of the bosonic side. And so as long as these two sets of degrees of freedom largely don't talk to each other, they're individually consistent, um, and everything seemed to work. And so, well, first thing the next morning, I headed into the lab. I explained what was going on to David and Jeff, and we spent the whole day trying to, find flaws in what was going in this proposal, and something had to be wrong. And we just failed miserably to find any problem whatsoever. And so over the course of time, we gained confidence that we'd indeed found the new E8 cross E8 string, as well as a second one independent of the Green-Schwarz one that had an SO32 symmetry. And because, this realization of how things worked stemmed from this conversation I was having with Ryan Rome, he soon joined our collaboration, and subsequently we became known as the Princeton String Quartet. Now, initially we just called it the hybrid string because we were sort of like grafting on, the bosonic string and the fermionic string into a single string. And then at some point, Jeff suggested the word heterotic, which is a term in plant breeding. Heterosis means hybrid vigor. It's the Greek for hybrid vigor, and it describes the feature that when you do cross-pollination of plants, that very often the daughter species combines all the best properties of the two parent species. And so it seemed like a perfect description of what was going on here, that by marrying together, by cross-pollinating the bosonic and fermionic strings, we got the best features of both. The gauge group you needed for the standard model and the absence of instabilities coming from supersymmetry. I should say also as another side note, around this time, so when it came time to write up our results and announce them in a brief letter, we submitted it to physical review letters. And physical review at that time regarded itself as sort of the guardians of purity of the English language, sort of the Académie Française of physics. And so initially they balked at our use of the word heterotic because they thought it was some kind of neologism like anion or axion, that we had just somehow made up. And so we pointed to them that it actually is a word in the OED. So it is a word in the dictionary, and so it should be perfectly allowable for us to use it. And so they let it through. So one of the final pieces of the puzzle was to understand what made E8 cross E8 and SO32 special from the point of view of string dynamics. I had spent much of the first bulk of this talk explaining that everything should come from the scale invariance and reparameterization symmetry of the string worldsheet. So how does that fit in here? Well, Ryan pointed out that the property of the Cartan torus that made these two groups special for Goddard and Olive is the self-duality of the lattice of allowed momenta on the torus. Basically, so for E8 cross E8, it's the statement that the root lattice and the weight lattice of the group are the same lattice. And so this property was needed in order not to have a global anomaly in conformal symmetry, a property known as modular invariance that was a large part of Greg Moore's presentation yesterday. So modular transformations are discrete conformal transformations. You can't reduce them continuously to infinitesimal conformal transformations, and so their validity is not guaranteed by the symmetries that the anomaly in current conservation is not a guarantor of the absence of anomalies in modular transformations. So the two special groups were precisely those two groups for which the string amplitudes were modular invariant. So this is just a depiction of the modular transformation in question, that you have two directions along the string worldsheet, and the string worldsheet is representing a one-loop diagram of string propagation, that you should be able to parameterize that world sheet with red and blue axes going one way or with the other way, and that those amplitudes should be equal. And this theme had a further variation in the analysis of the beta functions. So the heterotic string came first, and then afterwards I was involved in this analysis of the beta functions that yielded the space-time field equations. And so if you have these additional E8 cross E8 or SO32 currents on the world sheet realizing the space-time gauge symmetry, there are now additional terms that you can write down in the trace anomaly equations on the string world sheet that are associated to the Yang-Mills gauge fields. And so this is the associated term on the right-hand side of the trace of the world sheet energy momentum tensor. And this vanishing of this beta function turns out to be the Yang-Mills equations for E8 cross E8 or SO32 Yang-Mills gauge theory. However, there's yet another anomaly that can appear, which is that because this heterotic string has different left-moving and right-moving degrees of freedom, it's a chiral theory on the world sheet. And so there can be chiral anomalies on the world sheet. And indeed, the nonlinear sigma model, as it's called, the field theory, world sheet field theory describing heterotic strings propagating in some general background, that two-dimensional field theory has a variety of sigma model anomalies that one can discuss. And so in the work with Green and Schwartz and parallel work by Hull and Witten, those sigma model anomalies were analyzed. Just purely an anomaly in the consistency of the string world sheet formalism again. And what is the cancellation of that anomaly? It turned out to be nothing other than the Green-Schwartz modification of the symmetries that led to their modified anomaly cancellation. So you could even understand the Green-Schwartz analysis of anomalies from the world sheet point of view. So it really did seem at this time that the underlying symmetry structure, the underlying principle that gave you all of the structure of Einstein's equations and Yang-Mills theory and so on, that you would need for a unified theory, came from these world sheet considerations. So let me just recap what happened in this miraculous academic year, and then say a little bit about what happened beyond that year, and then wrap up. So as I was saying, in September 1984, August, I guess, they announced their result in a seminar. In September, the preprint came out, was the Green-Schwartz anomaly cancellation condition. And then a short 2 months later, we had this entire picture of the heterotic string. It really developed quickly. Just piecing together, this Goddard and Olive results and, what was understood of the Polyakov formalism. We also worked in the light cone gauge that was familiar to Green and Schwartz. And putting everything together happened very quickly. Things fell into place very quickly. And then in 1985, work that I was not involved with, which was a key milestone in the development of string theory, were the analysis of Candelas, Horowitz, Strominger, and Witten of solutions to these Ricci flatness conditions that gave you consistent string backgrounds. Such manifolds that satisfied that were called Calabi-Yau manifolds, and their properties launched a whole enterprise in connecting string theory, 10-dimensional string theory, to the real world we see in 4 dimensions. In April was the covariant quantization work that I did with Friedan and Schenker. So developing the whole formalism for how you do string perturbation theory in a general solution of the beta function equations, and how you construct the operators associated to the entire string spectrum, including the fermions. And then the beta function work was actually sort of contemporaneous, but the paper only appeared in June of that year. The description of how string theory how the world sheet consistency conditions of string propagation give you space-time field equations. So all of that sort of string theory was sort of launched, full-born in the span of 9 months from, you know, uh, um, from the realization that it could be a unified theory to a full-blown theory of unification. Now, that's not the whole story. It took us another 10 years. So let me just describe briefly what went on after this miraculous year. And it's the subject of a whole other talk that one could give, but I realize the hour's growing late. It took us another 10 years to understand that there's much more to string theory than just the string and its worldsheet. Zoology of other extended objects, now known as branes, D-branes, Neveu-Schwarz 5 branes, Kaluza-Klein monopoles. There's a pantheon of other extended objects. There's even sometimes an 11th dimension of space-time. And all of this additional structure seems to be essential for unlocking various non-perturbative phenomena that we know about, such as black hole physics and the Big Bang singularity in cosmology. And as a result of that, the fundamental dynamical principle is now less clear than it was at the end of 1985. Because even the fundamental degrees of freedom are in some sense mutable. That the string in one regime can become, you know, the string is sort of a descriptor, a description of the string scattering in regimes where the string interactions are weak, and so if you crank up the string coupling, as the string interactions get stronger, the branes get less massive, and eventually they sort of cross over, and the branes become light and the strings become heavy. And so what is the string in one regime can become a heavy brane in another regime, and vice versa. And all of these regimes are related by what are called duality symmetries. Duality is another overused word in physics, but okay. Two different string theories being related in this way by dialing up the coupling is called a duality. And these dualities relate all the previously known string perturbation theories. So the string that was developed by Green and Schwartz and their collaborators is related to the heterotic string by smoothly moving around in the parametrization of the background. And these features make it difficult, if not impossible, to follow our standard prescription for developing a theory that we've known now since, you know, Einstein, Maxwell, standard model, et cetera, that if what you thought was the fundamental object, namely the fundamental, the string, the heterotic string or the Green-Schwartz string, if that's not fundamental, but different ones are fundamental in different regimes of the configuration space, how do you begin specifying what are the sort of fundamental dynamical degrees of freedom and what's their configuration space? What are the local symmetries? Because the local symmetry for the Green-Schwartz string is different from the local symmetry for the heterotic string, et cetera. And even the space-time dimension can be anything from 0 to 11. I'm out of time for describing that, but basically, you know, people complain that string theory is on a 10 or 11 dimensional. Well, what's the operational significance of that? It's that there's a scale set by the string tension. And as you crank up the energy and scattering to that scale, you start seeing the excited states of the string. And you keep on cranking up the energy, and eventually you reach the Planck scale. And if the string is weakly coupled, there's a large gap between the string scale and the Planck scale. And then it's at the Planck scale that you start seeing quantum gravity. In particular, you start seeing small quantum black holes as being the excitation spectrum. Well, if string theory coupling is of order 1, you just have you know, field theory up until that scale, and then above that scale you have black holes. There are no, you know, remnants of an extra dimension or anything. You could have 4-dimensional physics up to the Planck scale, and then a spectrum of 4-dimensional black holes, and that would be all you would see. So this notion that string theory is somehow 10-dimensional is itself an artifact of a weak coupling description. and it really can be just about anything. So it has, within it, the capability of describing the four-dimensional world we see around us. And so, okay, but then the question is, what about this principle I've been telling you about throughout this talk of the string worldsheet is somehow fundamental and everything else is a consequence of that? Well, that has to be somehow relaxed. And the question is, what principle replaces it or generalizes it? The string principle was generalizing general relativity. Now we have to understand what generalizes that and accommodates all of these dualities. And we don't really know. Gauge gravity duality is another phenomenon that's appeared in the subsequent years, and that's yet another way of understanding what's going on beyond string perturbation theory. It's another step in the right direction, but it again, it privileges one particular brane. And basically, it's a large charge limit. It's saying, let me fill space-time with a whole bunch of d-branes of one particular type. Okay, and then what you find, if you look at it a bit, is that all of the other excitations, the gravitons, et cetera, are collective excitations of that particular gas of d-branes. So again, it's saying that, I can invent particular limits of the theory where I can understand things, in some more conventional framework. But again, it's not the whole story. And we definitely need some new ideas to tell us what this more general principle is. We've been scratching our heads since the mid-90s and making only modest progress. So that's about all I have to say. I'm sorry for running quite so late, but I thank you for attention, and I'm happy to answer questions.
Professor Martinec, thank you very much for your talk. In terms of questions, I'd actually like to go first. So in an article titled Superstrings, A Brief History, John Schwartz discusses how Edward Witten became a strong evangelizer of string theory after the 1984 work on anomaly cancellation, and how he thinks that string theory would have been accepted more slowly without Witten's push. In a similar vein, there's an article titled M-History of the M by M.J. Duff, and he discusses the pushback against membranes by string theorists in the 1980s, even after certain encouraging results, and over this change in Witten's M-theory paper, which appeared in 1995. So I was wondering, in a very broad sense, if you could say something about Witten's sociological in the field.
Yeah, so in terms of my own thinking, I was very much enamored of this idea of the string worldsheet as being some kind of underlying, and its consistency of the string worldsheet dynamics as being some kind of underlying principle that replaced the usual symmetry principles, local symmetries of gauge theory and gravity. And so that led us to a certain, bias or prejudice that anything that didn't fit within that conceptual framework, should be dismissed. And so a lot of, what I described here was as, those symmetries being a consequence of the string worldsheet. Well, the string worldsheet is a realization of perturbative string scattering. And so it's definitely an artifact of the weak coupling approximation. So, so the fact that that these other things like M theory that came along in the mid-90s and Duff's work on membranes and so on, I kind of dismissed all of that because it didn't seem to fit within this rubric of string worldsheets. And so you tried to quantize a membrane, you just got nonsense. You didn't get anything quite as nice as the Virasoro algebra and conformal symmetry and so on. That there weren't any nice scale invariant theories, so it didn't seem like there was a consistent membrane quantization. And so now the way we understand that is that in fact the membrane is a manifestation of this larger structure at strong coupling. And so, yes, it doesn't fit with perturbative string theory because it's an excitation in the non-perturbative regime where string theory is strongly coupled. And so fitting M theory, fitting membranes, fitting D branes, and asking like, what is the general principle from which all of these structures devolve? That's this large unanswered question that we've been struggling with, and it's hard. Simple examples, in gauge theory, there are examples of dualities in gauge theory that were worked out by Seiberg and Witten again in the 90s as a run up to this development of M theory. And once again, in writing down a gauge theory, writing down the Yang-Mills action, et cetera, you privilege a particular set of degrees of freedom, the so-called electrically charged degrees of freedom. And gauge theory, Yang-Mills Higgs systems have magnetic monopoles. They have magnetic degrees of freedom. And you can't write down a Lagrangian principle that simultaneously encompasses both the electric and magnetic degrees of freedom. The vector potential itself is a description of the properties of the electrically charged particles. And so if you have this sort of like democracy of all the different branes and strings, et cetera, and they all should somehow be part of the fundamental description, some branes are electrically charged and some are magnetically charged. And so if you're trying to, once again, write down some theory which has both the electric and the magnetic degrees of freedom simultaneously as part of the deep structure, it's not clear that there's going to be a standard Lagrangian. There's, this usual tools we use for describing such a theory, like Lagrangian field theory, just have obstructions. And so we need something else. And string perturbation theory sort of is a hint of that something else, but it's not the whole something else.
Thank you. I actually like. Could you say a bit more about like sort of attempts to go beyond 2D CFT? I remember reading your paper with Kutsasov on n equals 2, 1 heterotic strings a while back, namely the paper titled New Principles for String Membrane Unification. And what I found really interesting looking at the bibliography is that under started dating back to the 1980s, and people using, certain, complexifications of space-time and the world sheet. There's Green's paper, world sheets for world sheets. I remember Edwin has a paper, I think it's called The Search for Higher Symmetry in String Theory. I think it's like 1989. And he basically says that 2D CFT is like far too singular and that classical string theory really needs to be like, needs to be understood. And it seems that there's a lot of hints in the literature and a lot of attempts to do so, but not really succeeding in finding deeper underlying principles. Could you comment more on like, concrete ways of like doing that or attempts to do that?
Yeah, well, so that paper with Kutasov on um, was an attempt to regularize, in part was an attempt to regularize the world volume of a membrane. It was a string theory whose target space had 2 space and 1 time dimension. So it could be the world sheet of a membrane. But I regard all of that as kind of like some kind of exploratory idea that you haven't heard about it since then because it didn't go anywhere, or if you like, it's a nice idea, but it didn't have legs. And how it exactly fits into the sort of pantheon of string theory constructions, I don't know. I will say that I think the idea that looking for a standalone quantization of the membrane is a bit misguided. What we understand from the work of Banks, Fischler, Schenker, and Susskind, the so-called BFSS matrix model, is it came about as a way of synthesizing earlier ideas about membrane quantization into M theory. And one of the features of string theory, the idea that if you look at the string world sheet and you just lay down coordinates on it, radial coordinates, it looks like the way you relate, one coordinate isobar to another one is by a scale transformation going this way. Well, that's related by a coordinate transformation to a cylinder where these concentric circles are just the equal time surfaces. So those two descriptions are related by a conformal transformation. So the conformal invariance of the string worldsheet is a way of relating string propagation to short distance properties of the worldsheet. Now, and furthermore, if I have some worldsheet, say like this, and I lay down my coordinates and they're looking like this. Okay. This, if you warp your imagination, is related to a process that looks like this. The same sort of conformal transformation can map this piece of the plane with so this coordinatization of the plane is related to this coordinatization of the so-called pair of pants diagram, which has a string interaction here. And so, so the process by which strings split and split off other strings is related to the short distance properties of conformal field theory by this conformally invariant operator algebra. And there isn't any structure like that, any analogous structure like that if you tried to quantize a membrane. But the short distance singularities of the membrane have a similar feature that if you had a fluctuation on the membrane world volume, some short distance fluctuation, that would be associated to some violent excursion of the scalar fields that said where the membrane is in space-time, analogous to the string worldsheet coordinates. And a violent fluctuation of a spike on the membrane is just describing some other thing that's leaving the membrane, right? You have a bulk of the membrane is here. You have some spike of this, some spike in the scalar field. That spike is just describing something going away from the membrane in some other coordinate system. And so what was understood in this BFSS matrix model is you should really think of the UV singularities of trying to quantize the membrane is associated to the long distance propagation of particle-like degrees of freedom, like the graviton. Except, these violent short distance fluctuations are much more violent for the membrane as compared to the string. And so you really need some kind of strong coupling non-perturbative description of space-time gravity in order to make sense of how the membrane is quantized and how that fits in with all of the other objects that are in the theory in some kind of unified way.
Thank you for your thoughts. Are there any other questions?
Yes, thank you very much, Professor Martinec. That was an extraordinarily thorough and deeply compelling presentation, and it was thoroughly a pleasure to see. I thank you very much for your time. But I have a question regarding, so you were talking about the quantization of the gravitational the gravitational metric with regard to the world sheet, this world string sheet. I was wondering what your opinions are with regard to the apparent relationship between the world sheets and the two complex in loop quantum gravity, more specifically a spin foam approach or spin network approach of space-time, and whether you think that there's any interest or validity in quantizing space-time approach with regards to unifying some of the issues in non-perturbative quantum gravity in string theory.
Yeah. There. I'm not sure how to bring those ideas with, how to marry them with the set of ideas that come out of string theory. They tend to be much more related directly to working in 4 dimensions, and some other attempt. So there's sort of been if you want to think about sociology, there's a there's uh, a peer group within the theoretical community for whom the guiding star is Einstein's general relativity. And that the quantum theory of gravity should come from just understanding better how to marry quantum mechanics with general relativity. And so, if we could just find some slightly better set of variables to quantize, some slightly better parameterization of the configuration space, that we could do it. And string theory, as I was explaining, it comes out of the particle theory community, and for whom the idea that theories are always effective, and that as you go up in energy and reveal more structure, your low energy field theories become replaced by more complete theories that describe ultraviolet degrees of freedom. And so the idea that Einstein's theory could just be some kind of approximation to something deeper is very much in concert with the particle physicists' worldview, that Einstein's theory is just an approximation to something deeper. And so the spin foam ideas are this approach where you just say, well, we're just going to keep all the structure of Einstein's theory, and we just need to find these slightly better variables, and then we'll understand how to quantize it. Whereas string theory really, I think, represents quite a different departure. And it's not, if there's a way of using spin foam technology to describe string theory, it's likely a way of describing some particular corner of string theory. In the same way that twistor theory ideas became popular in the string theory community, because there were certain aspects of string theory that could be that could use the twistor ideas as tools for doing string computations, and thereby feed back into our understanding of twistors. But I don't think anybody in the string theory community would tell you that twistors are somehow fundamental, at least not in the way we're approaching things.
But isn't there an equivalence when you look at like a lattice of a world sheet of strings that if you sum over that collection of world sheets, it's bounded by strings. It is actually equivalent to a spin foam description. So in a sense, there is a way to perturbatively, scheme over UV variables. But I guess my question is more to the effect of, is there any benefit in unifying a quantization schema for the world sheets, which could have some sort of parallel to something that could be described as a spin foam, rather than, say, a formal adoption of the tenements of loop quantum gravity itself?
Well, it's possible. I said there were new ideas needed. Never say never. I was somewhat burned by thinking that the string worldsheet was fundamental, and that led me down a certain path. And it turned out that no, the string worldsheet's not fundamental. So it really, as I said, we're kind of at a loss as to what the unifying principle is, and I think we should keep our eyes and ears open to any mathematical framework that could both encompass what we know and extend it in new and interesting ways.
Much appreciation, Professor Martinec. Thank you very much. And again, it was a great honor to speak with you and to see the presentation.
My pleasure.
Are there any other questions? Oh, I see there's a question in the chat. Sorry, give me 1 second. Someone asked, let's see. What do you think are the prospects of finding a four-dimensional string theory that extends supersymmetry to fractional spins? Four dimensions seems to be the natural setting for closed strings with fractional spins, and I know some work that was done in the early mid-1990s, and Polchinski has a paragraph about the difficulties of finding such a theory, non-locality of.
Yes, yeah. Much of the structure of much of the toolkit of string theory, the mathematical toolkit, is looking at local operator algebras that describe strings, and you start and some of these anomaly cancellation conditions that I was talking about earlier have to do with the consistency of the local operator algebra and the idea of single valuedness of correlation functions. So you have to worry if you have fractional spins. Why are spins integer and half integer? It's because the worst that could happen is when you exchange two particles is you pick up a sign with fermions. But having something beyond that, fractional spins, or as Greg Moore was discussing yesterday, non-abelian braiding structures. It's the data that you have to keep track of to make sense of that is seemingly difficult to reconcile with locality structures that we would want in a description of particle physics.
Oh, I have a question.
Mhm.
Can I go?
Yes, please go ahead.
Thank you, Dr. Martinec, for a thorough and enlightening talk. My background is in mathematics, so this has been perhaps the best introductory lecture to string theory I ever had a chance to attend. My question is, given your extensive work in the field and your mention of questions of fundamentality, given all the dualities that arise in the theory, would you consider the most intriguing or underexplored mathematical structures in string theory or M theory? And alternatively, or building on that, could you share some thoughts on most intriguing interpretations of mathematical structures, physical interpretations of mathematical structures that arose in string theory? Thank you.
Yeah. One that springs to mind, one of the first things that sort of came to mind when you're asking your question was the connection between D-branes and K-theory that arose from work of Witten and Greg Moore and others in the early 2000s. That connects to the ideas that I was talking about earlier of renormalization group and renormalization group flows. So the idea is in K-theory is that you can sort of embed some bundle or sheaf structure and sort of embed it in larger and larger spaces, with the K-theory being somehow the quote unquote physical content or cohomological content of the stack of objects that you have. And that got realized in string theory is the bundles that were the objects in K-theory could be realized as the world volumes of D-branes. And the idea is that there are maps between these bundles could be related to strings stretching between the D-branes. And so one can map, questions in K-theory to questions about strings propagating around in collections of D-branes. And so, there's been a fascinating interplay over the last 40 years between ideas in mathematics and ideas in string theory, where at times physicists have borrowed ready-to-hand constructions and ideas in mathematics, like K-theory. There have been other times where string theory has provided new insights into mathematics. All the duality symmetries have been very fruitful in thinking about topology of four manifolds and things like that. And so if you ask what's the next big thing, I don't know. We need some structure. There's some dynamical principle that's just somehow missing, and dynamics and symmetries are deeply intertwined. And so I feel that maybe some of the work that's going on these days with deeper symmetries than just Lie groups may help us try to find some deeper structures that will give us a path forward. But look, if I had a promising idea, I would be pursuing it. But I'm here telling you that I'm personally at sea at the moment as to what the way forward is in terms of making progress on the fundamental structures that underlie string theory.
Thank you very much, Professor Martinec. This is fascinating and very exciting given recent progress in K-theory and like geometric Langlands.
Yes.
Thank you for that. Yep.
That was another example. I didn't mention it, but geometric Langlands is another place where these duality symmetries appear in an intrinsic way.
Thank you.
Yeah, if there aren't any other questions, I think we're going to end the talk here. Yeah, thank you very, very much for your time, Professor Martinec.
My pleasure.